In this video, my students of Quinta AF decided to give voice to the presentation of Thomas Maurice about decisions under risk and uncertainty, because that was a chapter that we faced during our lessons. The voice that we give to these slides is sometimes a talk, sometimes it's something being read. It depends on how strong this pupil felt about their English. But we are also aware that the slides have too many words for a speech, but that's the presentation that we worked on, and we had fun with it, and it was a nice guide to us as well. So here is Decision Under Risk and Uncertainty by Quinta AF dell'Istituto Calvi.
When you don't know the certain outcomes, we should make anyway a decision. We have to show all the possible outcomes with their possibilities. When you talk about uncertain outcomes, it refers to the risk. The uncertainty is different by the risk for the impossibility to list all the outcomes, and also we can't list their probabilities.
So a table or graph show the all possible outcome for a decision, and also the probabilities related with our outcomes. So we can measure and look the risk associated with a decision. Mm-hmm. So in a graph we can look the probability related with the risk of a decision that we have to take.
Okay. Now we can examine this bar graph, which has in the x-axis the sales, and in the other axis the probability. So we can see that we have some different probability for each one of the value of the sales. For example, in the first case we have a 10% of probability with a sale of 47,500. And for example, we have the major value when we have a sale of 52,500 with a probability of 30%.
For calculate the expected value, we have to follow this formula. In fact, the expected value is the sum of the P of I multiplied for the X of I, where X is the outcome of a decision, P is the probability, and N is the total number of outcomes.
An expected value doesn't give an actual value of the random outcomes, but give an average value of the outcomes, because the outcomes are compared with the possibility that may happen something. For example, if we have a percentage of 50%, we have to multiply them for the outcomes of 1000%, for example, and we have 500,000 euro. And this is another example. So the percentage is really important to give the right weight at the final average value.
In this slide we can show the variance, and we use the variance to measure the absolute risk and to find the probability of the expected outcome. The variance has the same role as probability. The variance is similar to frequency, but while the frequency is the square value of the variables, there are the value and the average value. The variance is the square value of the standard deviation. With the variance, we can measure the absolute risk and the dispersion of the expected outcomes. A higher result of the variance shows a greater risk that is associated with a probability distribution.
When you throw a dice, you have a 6 of chance to get each face of the dice. Each face that you could obtain is equivalent to a prize. If you want to find expected value, you have to multiply the probabilities with their prizes. Then you have to sum all the results. The last operation consists on dividing the sum with our 6 chances that are the 6 faces of the dice. You could do the same with 6,000 choices, and for the first case you could obtain 2,000 euros, and for the second 3,000, and so on. You have to sum all these results, and then you divide for 6,000 that are the total of choices, and you obtain the same results as for the 6 times.
This graphic shows two types of distribution, A and B. B has always an higher amount of profits, while A has less profits but with a bigger probability to make the higher profit, but also a bigger probability to make the less profit.
Connected with the previous slide, I can say the deviation standard formula, which is the square root of the variance. We use the square root to return to the previous other size, and higher is the standard deviation, higher is the risk, and so the opposite.
In this picture, we can see two graphs about two different probability distribution with different variances. In the first graph, distribution A, we have 15% probability to have a profit of 50, and only 5% probability to have a profit of 30 and 70. In the second graph, distribution B, we can see a lower probability than the first graph to have a profit of 50, but we have 10% probability to have a profit of 30 and 70.
Coefficient of variation is a standardized measure of dispersion of probability distribution. It means a measure of relative risk, and it's represented by the ratio of standard deviation and expected value. To explain this coefficient, we are made two examples. In the first example, we are the variation about 500, and in the second example, we are the variation about 100 for the same expected value. So we can deduce that in the first example the coefficient is more higher than in the second. So the risk will be lower in the second example because the ratio is more low than the first example.
The single decision rule didn't assure that profits will be maximized. They also don't eliminate the risk, but provide a method that includes risk in the decision-making process.
To take decisions rules under condition of risk, we have to evaluate the expected value rule, and we will take decision with the highest expected value, the mean variance rules, and we could have three possibilities. We can make an example. We take two risky conditions, A and B. If A is higher expected outcome and lower variance than B, we will choose B.
If we have identical variances, we will choose a decision with higher expected value. If we have identical expected values, we will choose decision with lower variance. Then we have coefficient of variance rule, and we will choose the decision with smallest coefficient of variation.
In this slide, we have an example of expected value, and these graphs represent the profit of a company in its three locations. We can see two locations that are that have the same expected value, but we have to see also the deviation standard, and the most favorable expected value is the location of Alonta, because the deviation it has a smaller deviation standard. So to choose the best solutions and outcome, we have to look the best expected value and the smaller deviation standard.
If we want identical probabilities each time, the expected value rule is more reliable to maximizing profit, and the average return of a given risky course of action repeated many times approaches the expected value of that action.
That is the case for a one-time decision under risk. There aren't rules to follow, because there are the necessary data to formulate a probability. So, to find the minor risk in a one-time decision, there aren't specific rules. But, as in art and science, we need the correct inspiration and a bit of luck.
We make a decision with the lowest risk value. The acceptance of the risk also depends on the individual and what they want in the future. For example, in a business, one person may want a certain situation and another may accept the risk. There is a person that derives utility from learning profits, and he is the manager.